Okay. It's my pleasure to be at CERI, and this is the second time I visit here. Yeah, and it's quite nice. And the weather is very good today, and I hope we have some time to trade outside, not in this room. Today we'll talk about the research of my groups doing thermo-mechanical models on subduction zones, and especially all of these today's models will include a lot of the model about the melting of the parameterized melting on the arc volcanism and how we did it and how it will affect the subduction model. So this is the schematic diagram for the subduction zone. And subduction zone is important for geophysics, and because this is the most important driving force for plate tectonics. The cold subducting lithosphere has the higher density than the overriding lithosphere, so it sinks down to the mantle, and at it sinks down, it acts as the major transportation for the hydrosphere and the biosphere, and it brings the carbon and the water into the mantle. So this is the most important recycling of carbon and the water into the mantle. And then this carbon and water, some part of it might go back to the surface with the arc volcanism. And the water is released as the slabs going down to the mantle, and this piece of the water in the mantle wedge lower the melting temperature in the mantle wedge and produce partial melting. And this partial melting eventually come up to the arc, becomes the arc volcano. And sometimes behind the arc, we have some region have the additional melting that is due to the spreading at the backup basin. And so one part of the talk is how we can generate backup basins. And the other part of the talk is most on how this melting here affect the behavior of the subducting slab and also the behavior in the arcs and in the four arc systems. So we look at how the melting is generated in the arc. In the subducting lithosphere, it's hydrated by some either hydrothermal circulation at the middle chain ridge or by the bending in the before the change. And so water can come into the slab, not just in the oceanic crust, but coming to beneath the oceanic crust. So the part of the subducting lithosphere is hydrated. And there are two main minerals can contain water in the lithosphere. One is the serpentinite, basically is anticorite, and the other is chlorite. And from the mineral physics model, well, we know that the stability field of these two minerals. So chlorite is more stable than anticorite in the high temperature. So it has go down to deeper depths. And as these two minerals becomes unstable, and they will transform to dry counterpart, and then water is released as fluid. And this fluid will penetrate the oceanic crust and migrate upward. And as it migrates upward, it will lower the melting temperature in the mantle wedge above. So without this additional water, the mantle wedge is completely solid. And with this additional water, the melting temperature becomes lower. And so now this region with warm color is the potential melting zone. And if this melting zone has high enough temperature, greater than the solidus, then the melt will start to form. And so we can calculate in the numerical dynamic model the temperature distribution of the mental wedge. So we need to include the effect of the water, how it transformed from the chloride to the dry counterpart, and where the terminus of the hydration front is. And then we can calculate the location of the melting in this region. And to the right is the phase diagram. This boundary is the chloride stability zone. And this curve is the melting solidus of the peridotite. And so the intersecting point is where the partial melting can occur in the mantle peridotite. So after we have some partial melting, and then it will generate the magma, and the magma has lower density, so it's buoyant and it will migrate upward. And this migration process is very complicated. And in the high temperature regime, this magma migrates through the flowing through the grain boundary. So it's a percolation. And so this is typically need to be described with a two-phase or porous flow. And after the melt reach to the low temperature region, and then all of the grain boundary is built, the grain boundary will be kind of, yeah, what did I do? The grain boundary will kind of be blocked. And so it cannot migrate through the grain boundary anymore. Then magma will accumulate and form magma chambers. And usually this is chambers location will be like either due at the rheology boundary from the ductile region to brittle region, or at the density boundary, usually at the base of the mohole. And these chambers, once it's big enough, it can further migrate upward by either diapiers or by dikes. And so the diapiering and the diking is the brittle fracture behavior or some plastic behavior. So the whole migration process is a very complicated physical process. So we don't want to deal with that in our numerical model. And so we use a parameterized model to describe the motion of the magma. And this is how we did it. So there is a subducting crust layer here, and beneath it, we have some finite thickness of the hydrated mantle lithosphere. And the mantle lithosphere has some temperature, so it has reaching to the chloride stability limit here in some depth. And so above this depth, the water is available. So we treated this region contains water, and we are not concerned about the amount of water, the concentration of water. We only consider with water or without water. And in the region with water, there's a potential of melting, and we can check the temperature and to see which region is melting. And for example, we got two regions that is under partial melting. Then by looking at the temperature and the difference with the solidus temperature, then we can estimate the degree of partial melting. And so now we have the two regions of partial melting zone, and we can calculate the area of the partial melting. Then we need to start to calculate how much magma can be generated from these partial melting zones. So we migrate the magma. We assume this magma will be produced at a constant rate. This rate, P, is a model parameter. We don't know the rate yet. And then it will generate the amount of the magma at this melting zone from the degree of partial melting, the area of the melting zone, and then the production rate of it. And then it will generate this amount of the magma. And this amount of magma then will be distributed into some fan-shaped zone. And we assume that this distribution is instantaneous. And usually the magma migration rate is, we don't know how fast it is, but we assume it's much faster than the motion within the mantle wedge. So because the motion in the mantle wedge is like on the order of a few centimeters per year, and we assume the magma migration is like 1,000 times, like meter per year, faster than the solid movement here. So we assume it's instantaneous, and we also assume that it is distributed evenly within this triangle zone. And this is a big assumption because we don't know how it would travel. And this triangle has some angle. This angle is also another parameter. Depends on how fast. If the magma travel very fast, this angle should be narrow. If magma travels slower, then this angle should be wide. And we don't know it yet. And so here we assume this is a constant angle. Then this triangle zone is for each single partial melting event. And we can accumulate the magma over time. So the magma is the capital M. Magma fraction on each location is a capital M. So the change of the magma fraction can be due to transportation and also the generation of the new partial melt. And in addition, we have to deal with the freezing of the magma. And we assume this freezing is like an exponential decay. And this decaying constant is time dependent. When the temperature of the region is cold, the decay will be faster. And when the temperature is high, the decay will be slower. And in addition, due to this freezing, then the local temperature will be increased and by the releasing the latent heat of magma. So this region will have the higher temperature due to the freezing of the magma. And this magma, it will, besides the temperature effect, it will also, some of it can go to the surface and become the arc. And so we can generate additional arc crust. The amount of the material go to the arc is, one is the ratio of R. Some of it staying in the mantle, R ratio staying in the mantle, and 1 minus R ratio go to the surface becomes the arc. So we can calculate the amount of the arc that is generated. So in the end, we have a few free parameters that we need to choose to generate a reasonable amount of magma and the reasonable amount of the arc crust. So first is the magma production rate. Is how much magma for each partial melting event can generate. And R is the ratio of the magma that is staying in the mantle or go to the arc crust. And theta is the angle of this triangle zone. And lambda is how fast is the magma freeze. And these four parameters, actually, we don't know their value. So we just try to use model and look at what the model output to quantify the potential range. And one of it, first test is looking at the Mariana subduction zone. Here in the Western Pacific, this is the Mariana subduction zone. And there are very detailed seismic tomography along this region. So we know the area of the crust, the arc crust along the transect. And by integrating the area of the arc crust and then also compare with the area of the typical oceanic crust, we can estimate the amount of the arc volcanism, how the arc crust is generated with time. So this arc has the thickness of the 13 to 22 kilometers thick, and typical oceanic crust is only 7 kilometers. And so it's being estimated that the arc production rate along this trench system is about 160 between 160 or 220 cubic kilometer per kilometer of the trench and per million years. So that is the goal that we want to generate our arc. And that production rate, if we look at our numerical model, that would be equal to this combination of the parameters. And the F melt is the degree of the partial melting that will be generated according to the temperature distribution in our model. And AI is the area of the partial melting. So these two parameters are the result of the thermo-mechanical model. So we cannot change that. But the other parameters, the R and the P, and especially the multiplication of the 1 minus R times P are these are free parameters so that we can tune it to match the observed amount of the crust. So we tune it, and then we try to use that to generate crust and also can generate the background spreading. So looking at the symmetry of Mariana system, you can see there is a symmetric shape of this remnant arc system. And on the center of it, this is the abandoned background spreading mid-ocean ridge. This is the now looking at this schematic model. So subduction zone along this Mariana system initiated about 50 to 40 million years ago. And when it becomes initiated, it will generate the first arc crust at about, this will last for about 10 million years. And after 10 million years, then the first sequence of background spreading start to happen. And this background spreading cut the arc, the first arc, by half. So there is the western part and the eastern part. The eastern part is still remains active volcano, and the western part become dead volcano. And now a new oceanic crust formed in between. And that is the oceanic basin in this region. And later, in the southern part of this trench system, this is the Mariana Trench, there is a second stage of background spreading. And this second background spreading split the arc again to form the western dead volcano and the eastern active volcano. And a new oceanic basin is formed here. So this peculiar configuration, in the north, there is only one basin formed. In the south, there are two basins formed, and they have the same overriding plate and the subducting plate. So they have the same plate history, motion history. So how we are wondering why there is region with only one backup basin and some region with a secondary backup basin. What is the what parameter control the effect? So usually when to generate backup basin spreading, you need a larger amount of the trench retreat. So here we look at the schematic diagram. We fix the upper plate. So and this allowed the trench to migrate to the ocean world. So the location of the trench is on this figure is moving to the right. And this allowed this part of the forearc to also move to the right and allow the space to a new oceanic basin to form in respect to the fixed overriding plate. And without the motion to the right, there's no space to form with the new backup basins. So the question is how you can have the trench retreat in the numerical model. And one way to do that is allow the a very cold oceanic lithosphere, and the density of this oceanic lithosphere will pull the slab downward faster than pull it forward. So the trench then will move to the right. And but this alone does not generate backup spreading, because to generate backup spreading, you also need to pull apart the overriding plate. If the overriding plate is a normal oceanic lithosphere, the strength is too strong. The amount of the stress is not enough to generate the backup spreading. So usually we need to have some initial weakness in the overriding plate, and this will allow it to have the backup spreading. And also, there another potential way to generate a very strong slab rollback is people argue that this is occurred in the very beginning of the subduction initiation. When the cold lithosphere, when it starts to subduct, this will generate a very strong toroidal flow current. And then a huge mantle counterflow will go into the mantle wedge. And this allows this region to open up very rapidly. But in the numerical model, to generate a very fast slab rollback, usually will require the upper plate is very weak. So you does not have any. So in this example, the lower plate, the subducting plate can be viscoplastic. So it means it has a finite yield stress. But the overriding plate cannot be plastic because the yield stress is too strong. It can only be viscous. That means the yield stress is effectively zero. Any small amount of the stress can generate a spreading in the upper plate. And in this kind of configuration, we can generate a strong backup spreading. And so this is another model has generated a strong backup spreading that they employed a very strong very high pore pressure due to the amount of the water released in the mantle wedge. So there is a very strong evidence suggesting the mantle wedge and the backup spreading that is due to the release of water or melt produce a high pore pressure and then weaken the yield stress in the region. Otherwise, you cannot break apart the you cannot break apart the overriding plate. So we consider the weakening due to the presence of magma, and the weakening can be decomposed into two parts. One is the weakening on the viscosity. The other is the weakening on the yield stress. So we think of the presence of the magma can reduce the viscosity by a factor of the FV, and can also reduce the yield stress by a factor of the Fy. And we can modify the FV and the Fy. So, and also to have allow the rollback, we cannot put a constant velocity boundary condition on the right, because usually when we have the constant velocity boundary condition on the right, all of the overriding plate will be under compression. So there is no extension environment to allow the backup spreading to occur. So we have to use a constant we have to use a free slip boundary condition that is on the right. So basically, this region will become a mid-ocean ridge, and the whole oceanic plate is moving by itself due to its density. So this is the simulation. And on the top here, this is the different type of rock, and in the middle, this is the amount of strain rate. The red color means high strain rate region, and the bottom here is the amount of the melt, amount of the magma in the region. I can play again. So first, the oceanic plates subducted and produce a large amount of the melt, and then reduce the strength of the mantle wedge. This allowed a very quick rollback. And sometimes the rollback can happen in a multi-stage, and this is not clear here. So we observe three types of behavior by changing the amount of the weakening due to the amount of weakening due to the yield stress, or amount of weakening due to the viscosity. And we found out that if we have a very little weakening, then we can have a subduction, but there is no backup spreading. So in the strain rate, you see only one single fault. And there is a tiny amount of the splay fault in the 4-arc region. And with a big enough the weakening due to the yield stress, then we start to see the Vega spreading here. And this will generate a new magma in the Vega setting. And if the Vega spread, if the yield stress reduction, weakening in the yield stress is very severe, so it's less than 1/4, then we can have the Vega spreading happens that is quite far away from the subduction trench. So in this setting, type 2, the location of the spreading is very close to the trench, typically less than 100 kilometers. So it will be located basically right on the volcanic front. And in this type of the type 3, the weakening is located on the left side of the volcanic front. So it will be further away from the trench. And this is the location of the Vega spreading we observed in the current present day Earth. Most of the Vega spreading is on the back side of the arc. So that's the big arc. It's not on the right on the arc. So we test the different parameters for the weakening of the yield stress and the weakening of the viscosity. And here, this diagram showing the location of the location of the spreading center with respect to time and to the trench. So the vertical axis is time. This is the million years. And the horizontal axis is the distance between the trench and the distance to the Vega spreading center. So like this diagram showing that the Vega spreading center starts at about 100 kilometers from the trench and move away to the left and become further and further away because the new crust is generated in between. And so we got the first, without enough weakening, we generate no Vega spreading. And with a little bit amount of general weakening, the Vega spreading occurred right at the arc. So it started at 100 kilometers. And with a much higher weakening, then we can generate the Vega spreading further away from the trench and 200 kilometers. And a few models like these two, let me go back, it's clear. A few models, we can have the second stage of the Vega, that is the jumping toward to the trench. And this configuration is very similar to the present day Mariana. I think this model is the first model that to generate a second stage of Vega spreading. So the summary is we need a weakening due to the magma, and the weakening effect on viscosity must be reduced by the viscosity must be reduced by more than factor by 50%. To produce Vega spreading, and the yield stress reduction must be less than 25%. No, must be less than 50% if the present day's configuration of the Vega spreading is to be reproduced. And if we use a very low yield stress reduction, and then we can produce a multi-stage spreading. And now let's change gear to look at the effect of the magma on the geometry of the subducting slab. And here, looking at the Central and the South America, there are three regions with the very flat angle of the subducting slab. So subducting slab usually is dipping like between 30 degrees to 90 degrees in the mantle. And in this region, here you see the black line is the depth contour of the slab. And the contour becomes very broad. That means the slab is going flat beneath the overriding plate. And some part of it, the dip is almost less than 5 degrees in this region. And so we want to study how this flat slab is generated and how the magma will affect these flat slab. And to generate flat slab, it will require that the mantle wedge has low pressure, hydrodynamic pressure, and the backside of the slab is a high pressure, and this pressure difference will push the slab angle to become shallower, and then you need to maintain this kind of low pressure configuration for a long time, and otherwise the slab will sink to a steeper angle due to its gravity. So to generate the flat slab, there are several attempts in the community, and usually they require reduction of the gravitational torque in the subducting slab. Then the most important reduction of the gravity is due to they remove the effect of the basalt to eclogite phase change. And basalt is less dense than the peridotite, than the mantle. So it provides a buoyancy force. But once basalt changed to eclogite is denser, and the eclogite is, in fact, it has a density higher than the mantle. So once basalt changed to eclogite, it will become a negative density, negative buoyancy. It will become make the slab higher angle than the typical basalt. So typically, to generate flat slab, people will try to avoid the basalt eclogite phase transition. They either not implemented this phase transition in the model, or they have somehow delayed the phase transition with non-stable phase rule. And the other choice is to decrease the viscosity in the mantle wedge to reduce the viscosity, and then also increase the thickness of the overriding lithosphere. That will allow the mantle wedge to have remain at a low pressure. So our goal is to develop a flat slab model with normal oceanic crust thickness and with eclogite metamorphism. So this is our configuration. The temperature profile and is according to the blue line is the overriding plate oceanic geotherm. So that's according to the observed plate age on this is a Cocos plate, Nazca plate. This is not Nazca plate. And to the right is the continental lithosphere. So we have an observation of the continental heat flux here. And also we have the observation about the thickness of the lithosphere. So we put in the temperature model here, and then putting also the borehole depth and some initial location of the slab here. And this was, okay, look at here. So we are looking at the face of the rock, and then the viscosity of the model, and then the change of the dynamic pressure. And you see that now our slab can go flat underneath the overriding lithosphere. And in this mantle wedge region, we constructed a consistent low dynamic pressure region. And this low, and beneath the slab, this is the normal dynamic pressure. So the range of the pressure difference is on the order of 100 megapascal. And we can calculate the torque, the bending torque acting on the slab due to this pressure difference, and also due to its own density. We can calculate that, and looking at the gravity torque is consistently smaller than this pressure difference torque. So this pressure difference torque can overcome the buoyancy force to make the plate angle nearly horizontal. And on top right is showing the length of the horizontal part of the slab, and we can achieve almost to 300 kilometer length of the horizontal plate. And actually, this is not compared with the present Chilean flat slab region. This is actually not enough. the present day is about the Chilean slab is about the flat region is about 400 kilometers. And we can change the different productivity, magma productivity. So here, this is the reference model. We use the PK. The exact value is not important because this is a parameterized value. We cannot compare it with any observation. So with this value of the productivity, magma productivity, we generate a flat slab. But with a 10 times higher of magma production, then you see this pink green color contour is the region of the magma. And this regional magma is slightly bigger than that in the early stage. Well, it's much bigger than this model in the early stage. And this will generate a larger region has the lower viscosity. And this higher region of this larger region of low viscosity does not allow the make the mental wedge flow into the tongue of the mental wedge and make the slab go to the normal deep angle instead of the flat. So by changing the amount of the magma, we found out that we need a very small amount of the magma generation in the Chilean region to make it flat. And in the so this indicates that there is either dry lithosphere in the oceanic part, so that there is not enough dehydrated water into the mantle wedge, or this part is much colder than the surrounding part, and so that it does not have enough partial melting. Okay, so how much time do I have? I think I speak too fast. Okay, and last is we are looking at where I'm from, the Taiwan tectonics. And Taiwan is located in Southeast Asia, located in East Asia, and it's between two plates. It's on the left, on the west is the Eurasian plate. On the east is the Philippine Sea plate. And the plate boundary in here has two plate boundary. On the northern side is the Philippine Sea plate subducted beneath the Eurasia plate. On the southern side is the Eurasian plate subducted underneath the Philippine Sea plate. So it's an opposite change of the polarity. And we are interested in the southern part of the subduction. So this part is the Eurasian plate subducted underneath Philippine Sea plate. And this generated a series of volcanoes. This is the Luzon arc. And eventually this Luzon arc that is in contact with the Eurasian continent and form a collision system and build up the island in Taiwan. So this is the simplified geological map of the island. There is a northeast, southwest stripe of the different layers of the material of the rock. So on the western part of it, this is called coastal plain. This is the youngest sedimentary sequence, and the green part of it is called the foothill sequence. This is the older metamorphic, lightly metamorphic sediment. And then in the center part of it is a highly metamorphic slab belt. And we think this is generated by the assumed Eurasian continental crust to the surface. And to the right, there is a very thin layer of the red color here, and this is called Yuli belt. This is the highly metamorphic ultramafic belt of the similar to ophiolite, and sometimes people think that there's a lot of the peridotite and some serpentinite and some of the metabasalt in this thin belt. So this is derived from the mantle. And then further to the east is the coastal range. This is the former region of the Luzon Arc. So this is a simplified geological cross-section. And the purple part of it is the second continental crust exhumed to the surface and build up the mountain. And here, the green color is the typical oceanic crust. On the right, you can have a sheeted dike, right? So we draw it in a vertical line. But to the left, this is showing a different orientation. This is, we call this part of it is the forearc of the Luzon Arc. So the forearc system is now being buried underneath the mountain. And why we draw this because if you look at the bathymetry, the trench is located here. And this is the Luzon Arc system. This is the volcano generated by the subducting of the South China Sea oceanic crust into the mantle generated volcano. And you see in this part of the ocean, the trench is north-south orientation, and the arc is also north-south orientation. So there is a constant distance between the trench and the arc. And then, but when you go to Taiwan, the distance between the trench and the arc actually shrink. And eventually the trench disappear. So we can only infer looking at the highest peak of the mountain. The highest peak of the mountain and the arc now almost only 10 kilometers apart. So there is a missing forearc. There's originally about 80 kilometers in east-west direction, and now become 10 kilometers. And so this forearc, where does it go, and where is it currently located is a mystery. And there are several conceptual drawings showing some of the forearc might be underneath this called the Central Range Mountain, of some of the forearc might be being squeezed beneath the subduction wedge, and some of the forearc might be buried partially under the arc system. So we want to use our numerical model to test it, and then also looking at how we can use the model to interpret our surface geological observations. So this is the typical schematic evolution of the arc continent collision in Taiwan. So in the beginning, they start from a long time ago, 32 to 80 million years ago, the South China Sea start to spread. And so it formed a mid-ocean ridge and some fracture zone. And between about 80 million years ago, the plate motion changed. So some of the fracture zones start to become a subduction system. And so the first change to form, and then the South China Sea oceanic crust start to subduct. And this subduction produced a Luzon Arc. So this Luzon Arc has an age about 18 to 17 million years. And after this South China Sea will be subducted completely into the mantle, and then the Eurasian continent start to enter the trench. And the Eurasian continent has a lower density, so it does not want to subduct into the mantle. So you will make the subduction fault, make it more stronger, and eventually you will produce an island in the region. And this island is generated with the scrape of the sediment. So this is like a accretionary wedge. But some part of the island is also formed by the second continental crust. That's not depicted in this simple diagram. And the collision starts when the when the Luzon Arc start to touch with the accretionary prism, and then generate a very severe deformation in the island. and some of it to form in the in the backbone range. And in this model, he thinks some of the fault arc go up toward above the continent. So he used this abduction model. So here showing the initial configuration of the different thickness of the crust. And this configuration is based on the seismic reflection data in the South China Sea, especially in this region. So present day, this part of the oceanic crust is already subducted. And so we infer the past history from the present configuration. So we took the data from here and think that in the 10 million years ago, this part is the same as here. And then we put in this is the strength profile, the upper crust, the lower crust, and the mantle. The upper crust has a very low viscosity. So this is strongly ductile in the lower layer. So now let's look at the evolution. Now this is the lithosphere. This is the rock type color, and the central part was showing the strain rate, and the lower part is showing the viscosity. Okay. Oh, can I stop? Or can I stop it? Okay. Well, now let's jump because I need to stop it. Okay. So this is in the beginning stage of the collision. Let's go back further. Now this is the end of the subducting South China Sea plate, South China Sea oceanic crust. And after this subduction, then the continental crust start to enter into the subduction zone, and now you will start to see a very severe deformation and the thickening of the oceanic of a continental crust. In the beginning, there is about 10 kilometers thick of the continental crust, and after it will resist subduction, then that means it will thicken in this region. So eventually, it will become the 20 kilometer thickness. And also the arc volcanism here will also weaken the oceanic crust in the west of the Luzon arc. That will generate east dipping thrust region, and then allow the Luzon arc to climb over to the fault arc system. So now the fault arc is being buried, pushed under the Luzon arc, and also under the newly created sediment. The black color is the young sediments. And also this fault arc when it start to deform, it will squeeze this red color layer. This is the serpentinized layer on the top of the subducting Eurasian plate. And now you are seeing the continental crust, and then serpentinized the mantle, and then fault arc that is sitting next to each other. And this is about the present day configuration. The mountain that is produced in here, that's due to the exhumation of the continental crust. And to the left, there is a region of the young sediment, and also the gray color is the older sediment that's been metamorphed. And then there's a layer of the red color, that's the serpentinized melange here, and then the young sediment, and then the arc system. Now we want to compare it with our present observation. So on the left is a tomographic result of the shallow region. And the green color shows the inferred seismic small hole from receiver function study. And in the continent region, you see that the mole hole become deeper and deeper and suddenly become shallower. And there is another jump in the ocean outside of the Luzon arc. And further to the east, there are less coverage. So actually, this part of mole hole is unreliable. And we can take this mole hole, compare with our model, and we see the deepening of the mole hole, and then sudden jump in the mole hole. In the mole hole, actually, we think we are not seeing the mole hole here. Mole hole is deeper. We are seeing the interface between the subducted sediment and with the forearc crust, and then further to the right. Okay, and on the top is showing the geological cross-section, and we can compare the mountain here is the second continental crust is here, and then the red color, the UD belt, the metamorphic serpentinized peridotite, and then the Luzon arc here is the magenta color, and in between some young sediments. So we got very, I think, the very good configuration, and you can look deeper, compare with another tomography model that is a more regional scale. So you go down to 300 kilometer depth, and the dashed line here showing the infrared subducted lithosphere, and we put in the subducted lithosphere is here. So we got a very good match on the subducting slab. And on the top, there is a region of the low velocity, and that is this region. And we think that this region is not, the low velocity is due to, first, the crustal material has low velocity. And second, you can look at the temperature here is elevated than the typical oceanic lithosphere. So some part of the velocity difference is due to thermal. Some part of it is due to competition. So in the summary, we found out that the Eurasian continental crust, when it's subducted, it becomes thickened and then it's humed at the center of Taiwan. And Luzon forearc crust is strongly deformed and it eventually become buried under the crust at the present day. And UD belt is a thin sliver of the serpentinized mantle that's being trapped between these two regions. Okay. I think that's the end. Thank you.
Will you please put back any of your simulations? I have a question regarding the black vectors that you plot on top. I think they show display.
They show the velocity, yeah.
That velocity?
This is velocity. You mean this?
Yeah.
Yeah, these are velocities.
Why the vectors, they look like it's pulsing?
Yeah.
Is that like a...
This is typical in the numerical model because we calculated the stress and then using the difference of the stress to calculate the deformation to get the velocity. And the stress is changing constantly with time. So the plane motion will start to wiggle a little bit with time. But because we are looking at 10 million years of evolution, so this wiggle can be like a 10,000 years time scale. So even we look at the present day GPS, it looks very stable, but actually it's changing a little bit with time.
Looks almost periodic. Yeah.
Yeah, I think is.
So this is something in your equations, basically, in the model.
Yeah, in our algorithm, I think, yeah.
But it's not related to time stepping and when did you... So I guess to do the simulation, you break down the million years in many time steps, right?
Right.
How to explain this? Okay. But anyway, It's not something that has to do on how you are extracting your visualization.
No,
within the time steps.
no, it's not a visualization issue. It's a we are not.
But what generates that weakness?
Because this has the more Coulomb failure in it. So there's an intrinsic nonlinearity in the model. And so sometimes when you stress is exceeds the more Coulomb yield stress, and suddenly the plate interface becomes weak, and you have an acceleration. Yeah. And so it's like an earthquake stick and slip behavior, but it's in a longer time scale.
I see. Okay. Thank you.
Could you speak to, with the Indian margin and the flat slab subduction, the along strike changes
Mhm.
we do have arc magnetism
Mhm.
and
Yeah.
just
Yeah. Yeah. This is a very interesting question because you see the flat slab here, they don't have volcanoes. Volcanoes are red. And that's because of the temperature. The flat slab region is colder, so there is no volcano. And but the question is how you can have this kind of lateral variation. So they got the same subducting oceanic lithosphere, the same overriding lithosphere. So some people has been argued that like in this part of the flat slab region, there is a subducting, there's a ridge that's being subducted. So people argue that the seeker oceanic crust here introduce additional buoyancy to make the slab more buoyant and so become flatter. But actually we think it's not, because seeker oceanic crust will produce a seeker eclogite, so make it even denser. So no, it's not due to the density effect. We think that it's due to the hydration effect. The seeker oceanic crust here is produced by higher degree of partial melting, and this higher degree of partial melting make it somehow the lithosphere even drier in this part, and this lower amount of the water make it this part of it less hydrated.
In some of your models, you show that you see formation of splay faults.
Yeah.
Have you specifically looked into the stability of these structures, or you don't look at this?
Yeah, we in this kind of study we didn't look at these smaller structure. Yeah, because the resolution here is about like each grid is like 2 kilometer by 2 kilometer, and in the accretion wedge usually you got 50 kilometer wide and 5 kilometers thick. So looking at this small fault is kind of in the limit of the resolution. We did some higher resolution model and the smaller domain, and we did look at the evolution of this splay fault. Yeah.
And do you see them being mostly confined near the surface, or they, like when they form, do they have a significant width?
The width.
The width of the fault, like
yeah. Because in this numerical model, everything is continuous, deformation is continuous. So the fault must have a finite thickness.
Yeah.
We don't have the discontinuous fault.
Right.
Yeah.
Well, I was just curious because for a totally different purpose, which is tsunami modeling, splay faults are very, even today, kind of there's no yet an agreement on how important they are in the generation of tsunamis. Because they are very small, they're not going to make a big difference even if they take up some slip. But anyway, it was just more about the formation of. Okay.
If you run the model enough, the slabs start to sink, or it just stop at the beneath of the oceanic sphere.
In this model, it actually reaches like a steady state. It becomes flat and up to 300 kilometers, and then you will continue as this shape. yeah, it won't become steeper, and you won't even make it more longer. No.
Because in the Juicy around the Korea area, there is a hypothesis about the flat slab.
Yeah.
And we can see some progressive arc volcano and
Yeah.
repeat of the arc volcano.
Yeah.
So I just wonder.
Yeah, if you
model this scenario.
Yeah, if you look at the geological literature, people have been proposing flat slab around the world, like in North America, Laurelite, and in tip of the South America, the Patagonia flat slab. And some of the proposal of flat slab is like 2,000 kilometers long. So we can never generate so long flat slab, but it might be due to our geology might be not good enough, or our model domain is not large enough. We don't know. Yeah.
Wait, any other questions? No. Well, let's thank Dr.
Thank you.
Good morning. Thank you. You have my number. So, this is wants to have a meeting.